Welcome back to the Deep Dive, where we turn stacks of sources into instant insight, custom-tailored just for you.
So if you've spent the last few years really deep in the world of large language models,
Yeah, trading them, fine-tuning, navigating things like Llama and GPT.
right, you already get the incredible power of text-based AI.
But, and this is the BI, if your goal is building something for, say, autonomous transportation or robotics, you hit a wall pretty fast.
You do. A text-only model just can't handle the messy visual reality of a busy street.
Or a factory floor, or even just, the glare on a traffic sign.
And that's really the critical pivot point we're digging into today.
Moving beyond text.
Exactly. We're moving beyond that linguistic frontier to dive deep into large vision language models, or VLMs.
So our mission here is to understand how these models get to true multimodal comprehension.
Right. How do they combine visual inputs, images, video with text? And we need to know why this is so essential now for real-world agents.
And how are the architectures different? And crucially, what are the safety hurdles they have to clear before we can, let them hit the road?
I think a lot of people in the LLM space, and probably many of you listening, felt like the potential was just limitless.
Just keep scaling up the vocabulary, add more parameters.
Exactly. But the sources we read make it clear there's a real ceiling for text-only models, a ceiling that's driving this huge industry shift to VLMs.
So what are those core scaling challenges? Why did we hit that wall?
There are two really foundational constraints. The first one is very practical.
The data.
The data. It's the finite supply of high-quality, diverse text data. We've scaled these models so hard that we've basically exhausted the good stuff on the public internet.
We read the whole book.
We have, essentially, and you get diminishing returns.
Okay, but the second challenge seems more profound.
I think it is, and this is where it gets so relevant for transportation and robotics. It's the inherent limit of a single modality architecture.
What do you mean by that?
Text is amazing for abstract concepts, for logic, but it fundamentally lacks embodiment.
It can't see the world.
Right. It can tell you what a chair is, but it can't intrinsically understand the spatial relationship between that chair and the table next to it.
Or what happens when light reflects off a wet road.
Exactly. A text-only model can't fully capture the physics and spatial reality of the world.
So the VLM is that missing link. It gives the AI eyes and grounds its abstract knowledge in physical reality.
That's a perfect way to put it. VLMs fuse the two modalities, and that gives them a much more comprehensive understanding of, objects, scenes, spatial relationships.
It expands what the AI can represent.
It gives it a richer, more contextually grounded view of the world, and that's exactly what you need when you're assessing risk and navigating an environment.
And we're seeing this translate into actual performance gains, right?
Mm-hmm.
The sources mention some big names getting better results just by adding vision.
Absolutely. I mean, think about the rise of models like CLIP, Claude, GPT-4V, Gemini.
All the big players.
They all demonstrate powerful reasoning on both visual and textual data. And here's the key thing. When you test them against classical single-modality vision models, the VLMs often win.
Especially on complex stuff.
Especially on tasks like zero-shot classification, because the shared linguistic understanding lets the VLM classify an object it has never seen before, just based on a text description.
Which a pure vision model just can't do.
It really struggles.
Yeah.
Which brings us back to the applications.
Right. For an autonomous vehicle, it's not enough to just see an object. It needs to reason about it.
Precisely. It enables capabilities like visual question answering or VQA.
So that's the ability to look at an image or a video frame and answer a complex question about it.
Exactly. You could ask the model, how many cars are getting ready to merge, and is the traffic light red for the turning lane? That's deep contextual awareness.
I get it. It's the difference between identifying a banana stand and reading the sign on the stand that says, bananas are $2.
Yeah.
You need both to get the full picture.
You need to fuse the text and the visual context for one final answer. Or in robotics, understanding an image of a person reaching for a tool on a cluttered workbench. You need object localization and intent inference.
Only VLMs can do that.
Only VLMs provide that kind of deep, contextually informed view.
Okay, so let's shift from the why to the how. The architecture has changed pretty dramatically. The early pioneers had to build these things from the ground up.
That's right. The older approach, you see it in models like CLIP and BLIP, they were trained from scratch.
And they used something called contrastive learning.
Right. The idea was to train separate encoders, one for the image, one for the text, and map them into a shared embedding space.
And contrastive learning is all about teaching similarity and difference, right? You minimize the distance between the image of a cat and the word cat.
And you maximize the distance between unpaired things, like the cat image and the word dog.
That sounds like it would take a ton of data and compute.
Astronomical amounts.
Mm-hmm.
And that's the major shift. Modern VLMs, Alava, Qwen2VL, the Llama 3.2 vision models, they leverage the pre-trained knowledge of LLMs as a backbone.
So that's the game changer.
A total game changer for efficiency and performance.
So instead of building a new brain, you're taking an already brilliant linguistic mind and just bolting on a high-performance visual unit.
That's a great way to think about it.
Okay, let's break down this LLM as backbone architecture. 3 main parts, starting with the vision encoder.
The vision encoder's job is just to look and analyze. It's usually a vision transformer, a VIT, or maybe a ResNet.
And it's pre-trained.
Heavily pre-trained on huge visual data sets like ImageNet or CLIP's image-text pairs. It extracts all the rich visual features, lines, textures, shapes, and turns them into a big tensor.
But that tensor is basically gibberish to the LLM. It's a completely different language from the token embeddings the LLM understands.
That is the exact challenge, and that's where the second component, the projector layer, comes in. The critical bridge. The universal translator. It's usually a pretty simple set of MLPs, multi-layer perceptrons.
And its only job is to translate.
Its only job is to map those super high-dimensional visual features into compact embedding tokens that are compatible with the LLM's text embedding space.
So it doesn't just pass the image along. It translates the image into the language the LLM already speaks.
That's absolutely correct. It lets the LLM process visual information as if it were just more text tokens.
Which is central to models like Alava and Qwen2VL.
It is. And the final component is, of course, the LLM itself.
Which is now the reasoning and generation engine.
Yes, it acts as the text decoder. And what's really efficient is that a lot of newer models don't even need a dedicated text encoder anymore.
They just use the LLM's own decoder.
They rely on the power of the original decoder for understanding all the tokens text and the new visual ones, and for generating the final output. GPT-4V, Flamingo, they're prime examples of this decoder-only approach.
That projector layer is fascinating, but it still feels a bit like an add-on. Are we moving beyond that, towards something more unified?
That's where things get really interesting. The next-gen architectures are treating all modalities as just tokens, right from the start.
A truly unified representation.
Exactly. Models like EMU3 use special separators like a start-of-vision token and an end-of-vision token to encode the visual stream directly.
What about transfusion?
Transfusion aims to process discrete text tokens and continuous image vectors at the same time inside a single unified transformer.
So a natively multimodal brain, not 2 brains talking through an interpreter.
That's the goal.
Okay, moving from architecture to deployment. If these models are for safety-critical apps like transportation, reliability is everything, which brings us to alignment.
And alignment complexity is it's magnified in VLMs.
Right. With text, you worry about factual errors, toxic output.
With images, the model can reveal sensitive visual details about people or places, or for an autonomous system, it might misinterpret visual context.
Like seeing a shadow and thinking it's a pothole.
Or misreading the fine print on a road closed sign. That's the critical concern.
So how are researchers making sure the model's behavior aligns with our preferences and safety rules?
They're adapting the reinforcement learning methods from the LLM world. So we're seeing RLHF, DPO, PPO, all being tailored for multimodality.
And I saw something called GRPO mentioned.
Yeah, generative reasoning preference optimization. It uses rule-based rewards to leverage the model's chain of thought abilities.
What's the advantage of a rule-based approach like that?
GRPO focuses on improving the internal reasoning process. So for a task like visual math, it doesn't just reward the right final answer.
It rewards the right steps to get there.
Exactly. It helps ground its logic in the multimodal data. But this requires a massive investment in data. We're talking about data sets with over 120,000 human-annotated preference pairs to get robust alignment.
And you can't align what you can't measure. The sources show the evaluation landscape for VLMs is just exploding.
It really is. We now have benchmarks in 13 major categories. But for anyone focused on agent systems, 3 of them are absolutely vital.
Okay.
First, visual reasoning. It assesses complex inference. Second, video understanding. Critical for autonomous systems because it tests understanding sequences over time.
Predicting motion, anticipating events.
Exactly. And the third is the most direct measure.
the dedicated robot and web agent benchmarks.
Right. Environments